Okay, so let's get started. Let me start with a few announcements first. So assignment 4 is due Friday. I will post the solutions by Saturday. What that means is no late assignments. But I also want to post the solutions by Saturday because the material covered on assignment 4 will be on the midterm next week. Now, I've said this before, but assignments should be submitted through Moodle in PDF. Okay? Makes it easier to mark. Otherwise, the marker has to spend a lot of time dealing with formatting and things like that instead of marking the assignment. All right, so then I guess you're curious about the midterm. So the midterm will be next Thursday, which is the 26th, I believe. The assignment will, the midterm, I'm sorry, will be in the DDM classroom of your respective institutions. And it will be during class hours, which means it's an hour and 15 minutes in length. Remember, if you chose not to do hand-in assignments, the midterm is actually worth a lot. So the exam, the midterm will be closed book. And you can bring in one double-sided letter size sheet of handwritten notes. And there will also be a formula sheet provided with the exam. So if, for example, it required you to solve an integral or a derivative, those would be provided. So you don't need to spend a bunch of time writing out a bunch of integrals and derivatives. And we'll have a review session on Tuesday during class. No, I will not make the formula sheet available beforehand. And the exam will cover up to chapter 4. Let me see what the section number is. It will cover up to chapter 4.4 included, i.e. not the last section which is the section on the Ruthian. So we don't need to do the Ruthian. But I hope we'll get through either today or on Thursday we'll be able to finish that material. Any questions about that? Oh, yeah, you guys always ask how many questions will be on the exam. Is that really relevant for studying? I think it will be 3 questions, plus or minus 1. Any more questions? Where did this Alright, so let's get back into it. Summary. Last time we introduced Hamilton's principle. And what Hamilton's principle told us was that the evolution of a system can be described by some function L that renders an integral called the action stationary. So Hamilton's principle says that S, which is defined, is called the action, and it's defined to be the integral from some time A to some time B of some function L that depends on the degrees of freedom, so the generalized coordinates and their velocities. And potentially time. So Hamilton's principle says that the evolution of the system is described by the function L that makes the action stationary. And so we know from variational calculus that L must satisfy the Euler-Lagrange equation for each degree of freedom. So the Euler-Lagrange equation, hopefully you didn't forget it in spring break, d by dt di L by di qi dot minus di L by di qi equals to 0. So there could be another term there if there are non-conservative forces, but we're moving towards just ignoring those and trying to understand the more deep fundamental issues or concepts of classical mechanics. Now from this very, very general approach, we asked ourselves, what could this function L possibly look like? And we found that for a free particle, L was going to be proportional some constant times the square, sorry, there's no m there, times the square of the velocity of the particle. And we determine that just by considering symmetries and properties of inertial frames of reference. So from very, very general assumptions about the laws of physics being uniform in space and direction, we concluded that this function L that describes the evolution of a free particle is proportional to the velocity squared of that particle. And so then we choose to call A a half m, because we know that when we take a bunch of derivatives, this 2 and the v squared will cancel the half. And then the fundamental constant that describes that particle we've relabeled from A to m. And so of course we identify that with the mass of the particle. And so the Lagrangian L, this function L, and it looks like a half mv squared, the familiar kinetic energy. But that's by observation. Okay? Now from D'Alembert's principle and Newton's second law and the principle of virtual work, we found that in general we can write L to be T minus V, where T is the kinetic energy of a system. The system can be one or more particles, and V is the potential energy. And so then we did many examples, I think, by now, of using this quantity L equals T minus V and solving all sorts of problems of balls rolling down inclines, masses on springs, pendula, etc. So I hope by now you're fairly convinced that this procedure, so identifying generalized coordinates, writing the kinetic energy and the potential energy so that you can build this function L, the Lagrangian, and then apply the Euler-Lagrange equation. I hope you're now convinced that that does give you indeed the equations of motion for the system. So hopefully you're completely convinced now that this is a complete way of doing classical mechanics. And we even saw that if we really want to go back and use the concept of forces, we can translate constraints using Lagrange multipliers, and then those Lagrange multipliers actually give you those reaction forces that maybe you held so dear in first year. Okay. So are people happy with that? Is there any questions about sort of the general philosophy, and are you convinced that this is a way to do classical mechanics that works? So if that's the case, and we've done the examples that back this up, then the second part of the course is going to move into a more theoretical understanding of L, and to try and get a little bit deeper meanings out of this framework for doing classical mechanics. So if you remember, when you do Newton's second law, so the tools that you learned in first year undergrad physics, you had a bunch of different tools in your toolkit that you'd have to sort of combine and figure out what's the best way to do it. So you can have a problem that, oh, maybe this is best done with the torques, or you have a problem this is best done with work and conservation of energy, etc. And they don't quite all fit together. It's usually one is better than the other. Conservation of energy might be more obvious than integrating Newton's second law. So this Lagrangian method, somehow it must unify all these things. It must unify the concept of forces and torques. And we saw that it did that with these generalized forces, where generalized forces may have units of newtons or they might have units of newton meters, so they could be forces or torques. We also saw some examples already of where conservation of energy and conservation of momentum sort of fall naturally into the framework. Maybe a lot of you missed the last tutorial on the Thursday before the spring break, but we did some examples there where conservation of momentum just naturally fell out of using this formalism. We never built in conservation of momentum. Conservation of momentum just came out. And so that's sort of the deeper understanding that we're going to look at and find more mathematical methods of solving these kinds of problems. And we're going to focus less on masses, on pendula and springs, and more on the framework and the math. In that spirit, let's move on to properties of the Lagrangian and look at some properties that this function L has. So one of the properties that sounds difficult to understand is actually quite easy is invariance with respect to what are called point transformations. So remember, we've been working with this set of generalized coordinates to describe the evolution of a system. And in general, it was a little bit arbitrary what are the best generalized coordinates to use, right? So in general, one can go from one set of coordinates to another set of coordinates. So the most general transformation from one set of coordinates to another set of coordinates is called a contact transformation. So from coordinates qi to coordinate system qi prime. So a contact transformation is something where the new coordinates, the qi primes, are functions of the original coordinates, q1 to qn, as well as the velocity of the original coordinates, generalized velocities, and then in principle time as well. So that's what we call a contact transformation. So maybe you are in a park, and you are a fixed coordinate system, you're sitting on a bench, and in front of you is a merry-go-round which is turning, and there is a coordinate system on that merry-go-round, and that coordinate system, to translate from your coordinates to the coordinate system on the merry-go-round, it's going to depend on the velocity of the merry-go-round, for example. So that's an example of a transformation that depends not just on the coordinates, but as well on the velocity. So a point transformation is just a special case. So a point transformation is a form of contact transformation. So there's a contact transformation that doesn't depend on the velocities. So that's the simple version. So a point transformation is just a change of coordinates. So for example, the transformation from Cartesian to polar coordinates is a point transformation. So in 2 dimensions, that transformation would be r. So in the polar coordinates, that's like the q prime. So it depends on the Cartesian coordinates, x and y. And it's given by the square root of x squared plus y squared. Right? That's how you go from Cartesian to polar coordinates for the radius. And similarly for the angle. It's the inverse tan of y over x. So point transformation maps a space onto another. The correspondence must be 1-to-1, and the point transformation must satisfy properties that, as physicists, we usually assume. But if you're mathematically inclined, then those properties are things like the Jacobian of the transformation must exist. What that just means is that you must be able to take the derivative of the transformation and it must be smooth and continuous and things like that. Okay? So, and you might actually argue that the polar transformation isn't, because what if x equals 0? Then y over x is infinite. But you can handle that and make it continuous by just defining the special case when x equals 0. So when r equals 0, theta is not really defined, right, in polar coordinates. So some of the properties of these point transformations, if I draw, for example, a square in Cartesian coordinates, then that maps in polar coordinates. So I'm doing something weird here. I'm putting r and theta on the x and y axes. So I'm treating these new coordinates r and theta as if they were, orthogonal Cartesian coordinates. So it's not so much a representation of space, so much as a representation of the coordinate space, some abstract concept of a particle being described by r and theta instead of x and y. So if you draw such a rectangle, then and you apply the coordinate transformation, then you get something that'll look like, thing in the notes I actually calculated where the points end up, but it kind of looks like a distorted version of the square. But what's important is that certain properties are conserved when you go from one space to the other in a point transformation. So lines that don't intersect in one space don't intersect in the other space as well. So here it looks like in the our theta plane, the two sides of the square are going to intersect. So that's probably because they shouldn't really map to straight lines, they map to curves, and so those curves actually won't intersect. So paths in one space are conserved in the other space. So two paths that don't intersect in one space won't intersect in the other space. If you really, really zoom in, and you make the little square that we're transforming from Cartesian coordinates to polar coordinates infinitely small, then it actually maps into a square in polar coordinates. And you can kind of see that, right? If I make it really, really small, it's going to be hard to tell the difference, even in polar coordinates, that it's not really a square. So the key here is that infinitesimals are preserved by point transformation. So a little square remains a little square. So those are properties of point transformations, and I'm just illustrating them here with Cartesian to polar. So that's important for the Lagrangian, because ultimately the goal in the Lagrangian is to maybe have solve for the motion, let's say, of a particle in our Cartesian space. And so that's going to be a line that it follows. And so that line will map onto its own line in the polar coordinate space. And because the infinitesimals are preserved from one space to the other, the Euler-Lagrange equation, which relates to infinitesimals and how they change with time, is also preserved from one space to the other. And so all of this is just to say that the Lagrangian description in one space will also work in any other space that's related by a point transformation. Or to say it really, really simple, it doesn't matter what coordinates you choose. As long as you choose a consistent set of coordinates and you write the Lagrangian in those coordinates, it will work. It's not like you have to write the Lagrangian in Cartesian coordinates and that's the only coordinate system where this way of describing physics works. No, it works in any system that's related to a Cartesian system by a point transformation. So you can always choose the most convenient set of generalized coordinates. Okay? So the conclusion is that the Lagrangian describes the system regardless of the choice of generalized coordinates. The Lagrangian is actually a constant. It doesn't depend on the coordinate system. The mathematical expression of the Lagrangian clearly depends on what coordinate system you're in. But the absolute value of it, if you evaluate it as a scalar, is independent of the coordinate system. So let's do an example, which is 4.6 in the notes. And this is the Lagrangian for a particle in a gravitational field. So the Lagrangian for a particle in gravitational fields in Cartesian coordinates is t minus v, so it's a half m times x dot squared plus y dot squared plus z dot squared and then minus V, and so the gravitational potential energy in Cartesian coordinates is minus M, or the potential energy is plus mgz, and then since it's minus V, it's minus mgz. So that's in Cartesian, right? So you apply the Euler-Lagrange equation to this. So you do it for each degree of freedom, and hopefully you've had some practice doing that. So you do, first you do it for x, right? So you have di-L by di-x dot, only the first term has an x dot in it, so that's mx dot, and you do a d by dt of that, that's mx double dot, and so you find mx double dot equals 0. There's no terms and x's in there. With x, similarly, you'll find that my double dot is equal to 0, and you'll find that, well, I guess the m's cancel, right? If it's equal to 0, and then you'll find that z double dot is equal to minus g. Oh, just cancel the m's. It's equal to 0. Of course, that makes sense, right? This is a particle in the gravity, so there's no acceleration in the xy direction, and there's a negative g acceleration in the z direction. So simply by transforming the coordinates, so remember T in polar coordinates, so the kinetic energy in polar coordinates, if you did all the transformations, and I think you've done that in the assignment, and we've also done it in class, the kinetic energy in polar coordinates is a half m r dot squared plus r squared theta dot squared plus z dot squared. Of course, the potential energy polar coordinates have a z in them, so it's still the same, and so the Lagrangian in polar coordinates is a half m times r dot squared plus r squared theta dot squared plus z dot squared minus mgz. And so now if you do the Euler-Lagrange equation to this, so you do di-L by di-R dot. So there's only one term with R dot, so that's going to give an mr double dot. And then it's minus di-L by di-R, so there's an r squared theta dot. And if I move it to the other side, I'll end up with mr theta dot squared. If you do the Euler-Lagrange equation for theta, you have only the one term with theta dots in it, and there's no terms with just thetas, so you'll get theta double dot equals 0. The m's cancel in the r equation, obviously. And then for the z equation, you'll also get that z double dot equals minus g. There's actually a mistake in the notes. There's an extra m there that shouldn't be there. And so that's just the equation of the same motion, just described in polar coordinates. Okay, so all that's to say that the Lagrangian is invariant to point transformation, and what that means is you can choose the generalized coordinates that make sense to you. And so that was the hardest of the properties to understand. But it has a very simple consequence, and the consequence is that you can basically ignore it and just choose coordinate systems that you like. Any questions about that? All right, so the next property is addition of Lagrangians. So let's say that we have two systems, System A and System B. So if we have two, let's call them subsystems. So we have two systems A and B with Lagrangians for each system that we'll call LA and LB. The total system can be described by L given by LA plus LB. We have two systems, each with their individual Lagrangians. You can describe them as a unified system, and all you need to do is add those two Lagrangians. So it's very easy to prove that, but if you just think about it, we've been doing this the whole time. When we calculate the kinetic energy for a system of two particles, we took the individual kinetic energies of the two particles and we added them. So we actually already did that. We already just assumed that that would be true. Same thing with potential energy, right? We have a particle that has gravitational and spring energy, and another particle with gravitational energy. Then the total potential energy that we used for T minus V was the sum of all the potential energies of the individual particles. So effectively, we've already done this. We'll just kind of sweep it under the rug, or we did see that often. I mean, it came originally from the term in the from Dalembert principle, where we had a sum over all the particles. But if you start from Hamilton's principle, then all we know is that the Lagrangian of each system satisfies the Euler-Lagrange equation. So since LA and LB are the correct Lagrangians for systems A and B, we know that the Euler-Lagrange equation is true for both systems. So for system A, the Euler-Lagrange equation is d by dt of di LA by di QI dot minus di LA by di QI equals 0. And similarly for system B, we have the same equation with LB instead of LA. So it's obvious that if you add the two equations, because of the property of derivatives, right, the sum of the derivative is the derivative of the sum, then it's clear that the function LA plus LB also satisfies the Euler-Lagrange equation, right? So we have d by dt of di LA plus LB by di QI dot minus di by di QI of LA plus LB equals to 0. So that's actually a very powerful statement, that you can break a system up into different components, or you can create a new system out of the various components. And with the Lagrangians, just add. That's kind of how particle physics works, right? The standard model is a Lagrangian between all the different particles that we know of, and it's the sum of all the possible interactions that we can think of. So we know of electromagnetics, so there's a bunch of terms in there that have to do with electromagnetic interactions, and mathematically it turns out it's allowed to add terms with other mathematical properties, and then we realize, oh, that actually describes the weak interaction very well, etc. And that's how the standard model actually works. It's just a big Lagrangian with a bunch of terms that are mathematically allowed. And so it's sort of these beauties of modern physics that it seems like any term that's mathematically allowed to be added to the Lagrangian seems to be in the Lagrangian. And that's led to the discovery of lots of new particles. Okay, so it's a very basic property, and a property that is already kind of used. Another one that we've also already encountered is multiplication by a constant. Let's say we have a constant k. So if L describes a system, so does k times L. That's again very easy to prove by looking at the Euler-Lagrange equation. So L describes for sure the system, so it for sure satisfies the Euler-Lagrange equation. So d by dt of di L by di qi dot minus di L by di qi is 0. And so hence if I multiply L by k, because the derivative of some constant times a function is the same as some constant times the derivative of that function, right? So that means that d by dt of di k times L of di qi dot minus di by di qi of k times L, that's equal to 0. Since k is a constant, it factors out. In fact, in the discussion that we had the week before spring break, when we looked at the Lagrangian for just a simple particle, we sort of arbitrarily chose a constant, an overall multiplication constant that gave us units of mass for the kinetic energy. So this choice of the overall constant that multiplies the Lagrangian is really just our choice of units of mass. So a choice of k is like a choice of units of mass. The only thing that really matters in the system is the ratio of the masses of the particles amongst each other. The overall mass of the particles doesn't matter in classical mechanics. In relativity, it doesn't matter. But in classical mechanics, it doesn't matter. So we can just choose the overall constant to be that gives us mass. And it's a fact that a very, very interesting and deep result that the choice of k that gives us mass in this description here is also the same choice that gives us the constant that controls how strong the force of gravity is. Right? The force of gravity depends on the mass of an object. We have two different ideas of mass. We have one, the mass that we've been dealing with so far, which is related to inertia. Ultimately, it's the thing that's in Newton's second law. It's like how much does a body resist acceleration or resist the force and result in acceleration. In principle, there's absolutely no reason that that constant m that is inertia has anything to do with how much gravitational force that mass can create. Right, so you have the Earth. If you push the Earth around, it has an inertia, and we call that m. If you're standing nearby the Earth, you feel the gravitational pull of the Earth, and that's proportional to the mass m of the Earth. There's absolutely no fundamental principle that tells us that those two m's are the same units and they're really the same thing. And the whole basis of general relativity is what's called the equivalence principle that equates those two masses, that equates inertial mass with gravitational mass. There's no a priori reason for doing this. And you can see it mathematically here that our definition of mass in terms of inertia is absolutely arbitrary. All the equations just work if we use a completely different definition. And it just happens to be what Einstein discovered, that that's the same mass that gives rise to gravity. And that gives you a very deep insight about the nature of gravity. Okay? So like I said, we're moving into a more theoretical aspect of the course. Hopefully you're convinced that L describes all the classical mechanics problems that you can think of. So now let's look at deep things that are embedded in this theory that just come out naturally. So here's another property that's kind of useless, you're going to think, but we'll see eventually it will be useful at some point. The addition of a total time derivative. df by dt. So the Lagrangian is invariant to the addition of a total time derivative. What I mean is, if L describes system, so does L plus df by dt. I really don't have to say anything about F. I just have to say it's a total time derivative. Well, I guess I have to say that F is probably a function of the generalized coordinates, generalized velocities. Since it's a time derivative, it's presumably a function of time. So you have a Lagrangian, and you can find something that is a total time derivative, and you add it to the Lagrangian, you haven't really changed the description of the system. This new Lagrangian, L plus df by dt, still describes the same system. And that's not so obvious why that would be true. So recall Hamilton's principle. I'm in trouble with my stylus. So Hamilton's principle just says that the correct L is the one that makes the action integral stationary. So let me do the action of our new Lagrangian, which is L plus df by dt. Well, it's the integral of the sum, so it's the sum of the integrals. Okay, well now, the first term is just the action that we're used to. But the second term integrates, right? that was the point. That's why it's a total time derivative, because to do the integral of a total time derivative, well, you just get the function. And so that's going to be the function evaluated at TA minus the function evaluated at TB. Now, L is given, or let's say L is the function that makes S stationary. So the fundamental principle here is that S is stationary, right? That is the fundamental principle of Hamilton's principle, is that L is the function that makes S stationary. But the fundamental concept here is that S must be stationary. So what is the condition for S to be stationary? So when we did the math, the condition for S to be stationary was that L must satisfy the Euler-Lagrange equation. But when we derived that, the first thing that we did was to figure out what the variation of S was with respect to the coordinates. So let's think again about the variation of S. What does that mean? So I can draw a path in time where I have TA and TB. So the variation, so the correct L is the correct path in time of our variables, Q. And so L, the correct path, is the one that maximizes this action integral. Right, so the system will choose the path of coordinates as a function of time that makes the action stationary. So to find that, we have to do the variation of the action and ultimately end up with the Euler-Lagrange equation. So remember, when we're doing the variation of the action, we're considering all the possible paths that the system could possibly take. Right, and the Euler-Lagrange equation just tells us how to find the correct path. So when we do the variation of S, we're actually considering different possible paths. Now the thing is, when you do the variation, all the paths have to start at TA and they have to end at TB. So the variation of the action is 0 at the endpoints. So for the variation to be 0 at the endpoints, that means the variations of the last two terms up here, f of TA minus f of TB, those will be 0. So when you take the variation of S, those two terms, f of TA and f of TB, just cancel, or they're just equal to 0. So you have to go back and look at chapter 2 and refresh your minds on how you take the variation of a function. And then you'll recall, or you'll remember, that in deriving the Euler-Lagrange equation, we explicitly use the fact that the variation is 0 at the endpoint. That's what canceled the term that was integrated by parts. And so for that reason, if you add a total time derivative to the Lagrangian, because when you take the action, that thing integrates to be a constant, and then you take the variation, that thing drops off. So it doesn't matter. So you can always add a total time derivative to the Lagrangian, and it will not affect the equations of motion. So if you can add a total time derivative, you can also add a constant to the Lagrangian, right? A constant, k, is the time derivative of kt. Right? So you can always add a constant to the Lagrangian as well. It's just a special case, and the Lagrangian is unaffected. In fact, we've encountered that already, and we already showed that when you add a constant to the Lagrangian, the equations of motion are not affected. Adding a constant to the Lagrangian, you saw, in the case that we did, is equivalent to changing the zero of the potential energy. Right? So I have that T minus V term. If I'm considering potential, let's say it's gravitational potential energy, if I change the origin of where I'm measuring gravitational potential energy, then I'm effectively adding a constant equal to GH, if H is the change in the origin, to my Lagrangian. So I'm adding a constant term. And so that physically makes sense that it doesn't matter, right? It's only the changes in potential energy that should matter. And then mathematically, you can see that changing the zero potential energy is exactly the same as adding a constant to the Lagrangian. We did that in the case of where we had, I think it was a disk rolling down an incline, and we had to write the gravitational potential energy of the disk. And we found it more convenient to identify where the disk made contact with the plane rather than find the center of mass of the disk. And we saw that that just changed things by a constant. Okay. So L is also unaffected by adding a constant term. That's just a special case. That's like changing the zero of potential energy. Huh? All right, next is a property that we've already derived. And we derived it in Chapter 2 for the calculus of variations so that we could use it here. So it's obscure when we did it in Chapter 2, and I told you, oh, this will be useful later. Well, it's useful now. So this is the case of the Lagrangian does not depend explicitly on time. So if you remember, we had a discussion of what it means to not depend explicitly on time. So that means that L is a function of Q1 to Qn, Q1 dot to Qn dot, but not T. So we can always check that by taking the partial derivative of di L by di T and seeing that if it's zero. So be careful. dl by dt is not equal to 0. The total time derivative of L with respect to t is not 0, clearly. The coordinates themselves in principle depend on time. So if you wanted to do the total time derivative, you'd have to use the chain rule And then of course the Q's depend on T, so you end up with a bunch of Q dots and Q double dots. So when we say the Lagrangian doesn't depend explicitly on time, it means that the letter T does not appear in the expression for L. So if you do dL by dt, you get 0. But that does not mean that dL by dt is 0. Okay, so did I write down? Yes, I did. So recall from chapter 2, which was equation 256. What we did is we took the Euler-Lagrange equation, just to remind you should go back and look it up when you're studying for this. But we took the Euler-Lagrange equation, and because dL by dt was 0, or in that case when we did it back then we were using x as the dependent variable, but we found that we could rewrite the Euler-Lagrange equation and integrate it away, and then what we found, now I'm going to write it with t's instead of x's, but we found that this term, the sum from I equals 1 to n of qi dot times dl by dqi dot, so that sum minus the Lagrangian, or minus L again, is equal to h, lowercase h, which was equal to a constant. Alright, so in equation 256, we had the sum from I equals 1 to n, and we had yi primes times dl by yi primes minus L equals constant, when dl by dx equals 0. And that's what we did when we were doing with x and y. And now that we're doing it with q's and t's, this is the equation that we get. And this is actually a very important equation. And so we're going to examine this a little bit more. So when the Lagrangian does not depend explicitly on time, you can build this a priori complicated looking expression, and that expression will be a constant. And I thought it was good when things are equal to constant because it makes the equations easier to solve, right? Here we have a qi dot, or a sum of qi dots equal to a constant, so that's going to be a first order differential equation in the qi dots. Remember, normally the Euler-Lagrange equation gives us qi double dots, right? Because you have a d by dt of dl by dqi dot. So ultimately you end up with second order time derivatives. So the reason why this appears like it could be appealing is that it's first order derivatives in time. So this quantity h, let me just rewrite it the other way around, to define to be the same thing, from I equals 1 to n of qi dot dl by dqi dot. So you sum over all the degrees of freedom and then subtract L at the end. That has a name, it's called the Jacobi integral. And it's constant, so h is constant if dl by dt equals to 0. You can always calculate this quantity, but it's only constant in the case of dl by dt equals to 0. And what we'll find is that this constant is actually very useful. It's related to what we call later the Hamiltonian, and we'll label that with a capital H. And the Hamiltonian is a little bit different, but it's basically the same. Alright, so it looks obscure and annoying to calculate. So maybe I should make one more comment here. So h is constant if dl by dt is 0. And we proved that back in chapter 2. So I'm not going to prove it again. Alright, when we proved equation 256, we proved that this was true. So for H to be constant, if diL by dt is 0, that also means that dH by dt is 0. Right? For H to be constant means it doesn't change with time. So that means the time derivative is 0. So that's interesting. This is a partial derivative, diL by dt. So L is not constant with respect to time because the Q's change with time. And H depends on the Q's. However, since H is a constant, dH by dt is equal to 0. So somehow the Q's are changing, right? The Qi dot in the expression for H could be changing with time, but somehow they cancel each other out so that the total H doesn't change with time. So diL by dt is equal to 0, but dL by dt is not equal to 0. And so then dH by dt is equal to 0, if diL by dt is equal to 0. So don't mix up what's a partial and what's a total derivative. So let's have a look at this quantity H, the Jacobi integral, for a specific case. So let's consider H when we're going to make two assumptions. First assumption we're going to make is that the kinetic energy is quadratic in the velocities. So we're going to assume that the kinetic energy T can be written as a sum over two different indices, J and K, of AJK, QJ dot, QK dot. So we're going to assume that T is quadratic in the velocities. And so we know it's quadratic in the velocities in Cartesian coordinates, right? And we know it's in polar and spherical as well. But this is often true. It's not always true, but it's often very true. Right? And the second assumption we're going to make is that the potential energy does not depend explicitly on time. I'm sorry, that it doesn't depend on the velocities, not time. Or I, let's just call it I, it doesn't matter. So making two assumptions. One, the kinetic energy can be written in the kind of way we like to write it anyway. And two, the potential energy doesn't depend on the velocity. That's generally true as well, right? The only case where we've seen the potential energy depend on the velocities is when we did electromagnetics, because the Lorentz force depends on the speed. And so we have to use the generalized potential. But all the other sort of potential energy that we're used to, like springs and gravity, those never depend on the speed or the velocity. So they're not that restrictive of assumptions that we've made here. So given these two assumptions, so di V by di Qi dot is equal to 0, that means that di L by di Qi dot is equal to di T by di Qi dot. Right? That's like saying di by di Qi dot of T minus V equals that. Right? Because di by di Qi dot of V is 0. We've assumed that. So that tells us that di L by di Qi dot is equal to di T by di Qi dot. And why do I care? Well, I care because the term here in the Jacobi integral has di L by di Qi dot. So I'm interested in expressing that term. Alright, so consider di L by di Qi dot. That's di T by di Qi dot. That's di by di Qi dot of what we have for T. What we have for T, well, we said that T can be expressed as a half sum over J, sum over K, A, J, K, Q, J dot, qk dot. Now, if you're not convinced, you should work this through. But I have a double sum here. So when I take the die by die qi dot inside of the sum, right, the sum goes from jnk all the way up to n, from 1 to n. So somewhere in that sum is a term when j equals to I, right? Maybe qj, or the q's are x, y, and z. So let's say I'm doing the qi is for x, so it's die by die x dot equals a half of the sum, and then inside the sum, the qj is going to at one point equal x dot, and the qk is at one point going to equal x dot. And so when I take the partial derivative with respect to x dot, I'm going to pull out the specific term where the j or the k is equal to I. If you don't believe me, you can go and write out the sum, the double sum. It's not that big for one particle in Cartesian. But what you'll find is that when you take this derivative, you're going to get 2 times the same term. You're going to get a half the sum from j equals 1 to n of a j I q j dot plus the sum from k equals 1 to n of a I k q k dot. So the first sum, you've pulled out the term when qk equals to qi. So the term in front of the qk when it's equal to I is qj dot times AJI. And the second term is the same thing the other way around. You're pulling out the term when j equals to I. So of course now, the kinetic energy, the AJK coefficients are symmetric in J and K. Alright, so AJK is equal to AKJ. So these two sums are the same thing. Right, so it's a half times one thing plus itself again, so it's just the same as one of them. So that's equal to the sum from J equals 1 to n of AJI QJ dot. So maybe it sounds confusing to do it that quickly, but I assure you if you write it out with an example of using x, y, and z's, for example, you'll find that this is in fact correct. And with some practice, it actually is pretty natural. Alright. So we found that diL by diqi dot is the sum of AJI QJ dot. Let me just use the notation from the notes so it's not confusing. So in the notes we actually chose the other term, we chose the K term. I apologize for doing that. AIK. That way I don't have to worry about messing up the orders of the Q's and the J's and the I's. But if you had the previous term, it'll be fine. Alright. So what we really need in the term H is we need the sum from I equals 1 to n of Qi dot times diL by diQi dot. Okay? So that's the sum from I equals 1 to n of Qi dot, and then the diL by diQi dot we just calculated, that's the sum from k equals 1 to n of AIK QK dot. So if I can just make it pretty, I can just put the two sums together. So I have the sum over I to n, the sum over k to n of AIK QI dot QK dot. So that term that's in the Jacobian integral is equal to the sum from I and the sum from k of AIK QI dot QK dot. Well, if I look up here again, if I just call Ji That's actually the definition of the kinetic energy. It's just twice the kinetic energy. Right? The indices are just dummy indices that disappear after you've done the sum. So the fact that I've called down here, I have an I instead of a J, that's irrelevant. So this is equal to 2T. It's equal to twice the kinetic energy, right? T was a half of that, and so the thing that'll be half is 2 times the kinetic energy. Any questions about that? So what this means so H, which was defined to be the sum from I equals 1 to n, qi dot diL by diqi dot minus L, that's equal to 2T minus L. So that's equal to 2T minus T plus V, T minus V, sorry. Right? L is T minus V. That's 2T minus T is 1T, and minus minus V is plus V. So H is T plus V. So what is T plus V? The kinetic energy plus the potential energy. Well, we call that the total energy. And we said that H is constant if diL by dt is 0. So the total energy is constant if diL by dt is 0. Well, we have a name for that, and that's just conservation of energy. So H is equal to the total energy. Remember, that's if diV by diQi dot equals 0, and T is equal to that double sum. Right? So if the potential energy doesn't depend on the velocities, which it usually doesn't, and the kinetic energy is quadratic in the velocities, which it usually is, then H is the total energy. Now, if diL by dt is equal to 0, then H is equal to a constant. And so we call that conservation of energy. So conservation of energy is built into this description of mechanics. That's really cool. We never said anything about energy. In fact, we never even defined the concept apart from kinetic energy and potential energy, but we never envisioned this idea of this total energy thing being conserved. And so we see mathematically that under certain mathematical conditions, namely that the Lagrangian doesn't depend explicitly on time, then total energy is conserved. And you see that that somehow relates symmetries in time to conservation of energy. Because if L doesn't depend explicitly on time, then I can shift time backwards and forwards by a constant, a translation in time, and the energy is still conserved. So there's some symmetry of the Lagrangian in time that's related to this conservation of energy. If L depended on the absolute value of time, like at exactly what time we are, then energy would not be conserved anymore. And that makes sense. Right? If gravity, for example, changed with time, then motion in the gravitational field wouldn't conserve energy. So not only is this a very philosophically important result, but it also allows us to solve problems in an easier way. So remember that I said that it's going to be appealing here that we have an expression that's in the first order derivatives, so it depends on qi dots, not qi double dots, and it's equal to a constant. And so somehow that must be easier to solve than a second order differential equation. So for a situation with 1 degree of freedom only, this leads to being able to write the equation of motion as an integral. Now remember, integrals are always easy to solve because you just give them to a computer. If the question is, can you integrate this, the computer will always say yes. You know, well behaved. You give it a differential equation, the computer might say, well, it's kind of hard. But an ordinary differential equation can always be solved as well. But an integral can be solved even easier. So let me show you that you can indeed write the solution to a problem. So what I mean is I can write q as a function of t equals some integral. So proof, but not very difficult to prove. So we have h equals t, so t depends on q dot, and then v will not depend on q dot, right? We said specifically that the v can only depend on q, but it can't depend on q dot. That was the condition for energy to be considered. So in principle, you can invert this. So you can invert to get q dot as some function of h and v. Right, I just bring the v to the other side and then divide by 1/2 m, for example. So if I can write q dot equals some function of the constant h and the potential v, which depends on q, that's really like saying dq by dt equals h minus v of q, right? So that means that dq equals h minus v of q dt, the separable differential equation, or the integral of dq over h minus v of q is equal to t. I guess on the notes I should have an integral for that as well. Alright, that's an integral that you can solve. Technically, this gives you t as a function of q, and then you'd have to invert that to get q as a function of t. Right? But that's a problem for mathematicians. Here it's clear that we can write it as an integral, and as physicists we're satisfied. So let's do an example where this is true. Let's solve a problem using this novel concept of conservation of energy, or h being a constant. So example 4.7, let's say we want to find the period t. Okay, it's confusing. Let's call it find the period of a simple harmonic oscillator. So for a simple harmonic oscillator, we've seen this before, the Lagrangian is the kinetic energy. So simple harmonic oscillator has 1 degree of freedom, right? So let's say it's just, moving along the x direction. So we have kinetic energy is a half mx dot squared minus the potential energy for a simple harmonic oscillator, which is kx squared, so half kx squared. So note, diL by dt is equal to 0. Hence, h, which is t plus v, is equal to a constant. Now be careful, h is only equal to t plus v if t is quadratic in the velocity and v doesn't depend on the velocity. Yeah. The case here. So h is indeed t plus v and it's a constant. And L clearly does not depend explicitly on time because there are no t is not in that equation. Right? So if that's true, then I can evaluate what my constant h is. So if the simple harmonic oscillator started at rest at position x naught, then the total energy of the system is whatever the potential energy was before you let the system go, so it would be a half k x naught squared. So t plus v is equal to a half k x naught squared. So t is a half m x dot squared. V is a half k x squared. And that's got to be equal to the constant, which is a half k x naught squared. So that means the halves just cancel, right? So I can write, I can write m x dot squared equals k, that's equal to k times x naught squared minus x squared. So I can write x naught is the square root of k over m times x naught squared minus x squared. That's dx by dt. And so I can write that dx over that square root, k over m x naught squared minus x squared, that integral is equal to, well, let's call the period t. So if we really want to know the period t, this has to be a definite integral. So if I go from the initial position x naught to 0, so picture a spring, right? You stretch it by a distance x naught. It's going to travel to 0, then it's going to travel to minus x naught, then it's going to go back to 0, and then it's going to go back to x naught. So it takes 4 times that time to get the period. So the period is 4 times the integral from x naught to 0 of dx over x squared. Of course you knew this, right? You knew how to find the period of a simple harmonic oscillator using conservation of energy. We just did it formally with equations, with the f of x and h. But you knew how to do this, I hope. So in the cases of 1 degree of freedom and conservation of energy, you can always solve the problem and write it down as an integral. That integral might be difficult to do, but who cares? We're not mathematicians. Okay? So let's see. Well, let me finish this up here. A couple more sections. Next, are there any questions about that problem? Or? So next, let me talk about cyclic coordinates. This is a very important concept. So sometimes L does not depend explicitly on some of the coordinates. It'll depend implicitly on the coordinates because L typically depends on all the velocity of the coordinates through the kinetic energy. But it might not depend explicitly on the coordinates themselves. Sometimes L does not depend explicitly on certain coordinates. We call those coordinates cyclic. So what we mean is Qj is cyclic if diL by diQj equals to 0. That's the definition. So L depends presumably on the Qj dots through the kinetic energy, but it may not depend on the Qj. And if it doesn't, we say that that is a cyclic coordinate. Well, the Euler-Lagrange equation must still be true, right? So the EL equation must still be true for Qj. So the Euler-Lagrange equation is d by dt diL by diQj dot minus diL by diQj equals to 0. Now the second term there, that's 0. Oops. If Qj is cyclic. That's by definition. Right? So that second term is 0 for cyclic coordinates. Hence, d by dt of diL by diQj dot is equal to 0. Well, remember, what does it mean for the time derivative of something to be 0? That means that thing doesn't change with time. So if that thing doesn't change with time, we also say it's constant. So that means that diL by diQj dot is equal to a constant. And that presumably also makes the equations of motion easier to solve, because dl by diqj dot is now going to depend only on qj dot. It's not going to have qj double dots in it because we don't have the d by dt anymore. So again, we're going to end up with some sort of scenario where you have qj dot something 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 equal constant. And so qj dot, at worst, is going to be a first order differential equation to solve. So that's very nice. The other thing you notice is this dl by diqj dot appears often, right? We had a dl by diqj dot when we did this Jacobi integral. Right? The Jacobi integral has in it a dl by diqy dot. The dl by diqy dot does turn up quite often. And in fact, it's a constant in certain cases. So we just define this as Pj. We define that to be dl by diqj dot, regardless of whether or not it's a constant. And it'll be clear later why we call this Pj. But basically, for every Qj, you can do dl by diqj dot, and that defines a new variable that we call Pj. And it turns out that variable is constant, so Pj is a constant if Qj is cyclic. So let's get a deeper insight into what that Pj could possibly be. So example 4.8. Same example I think we already did in this lecture. Particle in a gravitational field. Find conserved quantities. When I say conserved, I mean constant. Things that are constant. So what are constant in the motion of a particle in a gravitational field? So we start by writing the Lagrangian out for the system. So the Lagrangian is a half m x dot squared plus y dot squared plus z dot squared minus mgz. So let's start with cyclic coordinates. So how many cyclic coordinates in this Lagrangian? We have two cyclic coordinates, x and y. The Lagrangian does not depend explicitly on x or on y. It does depend explicitly on z. The last term has a z in it. But there are no terms with x's or y's in them. Hence, we expect dl by dx dot should be a constant. And we expect that dl by dy dot is equal to a constant as well. So let's look at dl by dx dot. Well, dl by dx dot is dy by dx dot of a half mx dot squared, which is just mx dot. Right? You pull down the 2, cancels the half. Same thing with dl by dy dot, which needs to be a constant, and that's going to be, if I do take the partial derivative, I get my dot. And those two things are constants. And then now maybe it's obvious why I decided to call those things Pj. So in that case, we would have Px and Py. And those are the x and y components of linear momentum. So we found that x and y components of momentum are conserved, and that makes total sense, right? Particle moving in a gravitational field The z component of the momentum is not going to be conserved because things are going to be accelerating downwards. Or there's no forces in x and y, so we totally expect the x and y components of the momentum to be conserved. And again, this is something that just falls out from this framework. We never made any assumptions about the properties of momentum. We never even defined what momentum was, and yet we found out conservation of momentum just comes out of these equations, just based on symmetries of the problem and the mathematical formula in mind. There's one more conserved quantity here, right? So there's the two cyclic coordinates, but then L does not depend explicitly on time. So we expect the Jacobi integral h to also be conserved. And in this case, the potential energy does not depend on the velocities. The kinetic energy is quadratic in the velocity. And so the Jacobi integral is equal to t plus v. And that is conserved. And so energy is conserved in this system. So we have a third conserved quantity. So we have di-L by di-T equals to 0, hence H is conserved. So I could write H as T plus V, but let me just go ahead and write it out the long way. So H is the sum, I equals 1 to 3, Qi dot times di-L by di-Qi dot, and then minus L. Alright, so I have to do the sum. So the first term, so Qi is going to be equal to x, y, and z. So the first term is when Qi is equal to x. So I have x dot times di-L by di-X dot. And di-L by di-X dot was mx dot, right? Di-L by di-X dot over here was mx dot. So I have x dot times mx dot, that gives me mx dot squared. Same thing for y, my dot squared. Now z we didn't actually calculate, so I'm going to have a z dot. I have to do di-L by di-z dot. Di-L by di-z dot is mz dot. Mathematically it's the same, it's just not a constant, but still mz dot, right? And so it's z dot times mz dot, that's mz dot squared. Okay? Now minus L, so it's minus a half mx dot squared minus a half my dot squared minus a half mz dot squared, and then it's minus the minus mgz, so it's plus mgz. Okay. So I'm grouping the terms, so the x dot squared, I have 1 mx dot squared minus a half mx dot squared, so that's a half mx dot squared, and same for all the other three. So I have a half x dot squared plus y dot squared plus z dot squared plus mgz. So it's indeed equal to t plus v. So H equals T plus V is conserved. So conserved and constant are pretty much synonyms. And so I think I'll stop here. There's a little note in the notes about how this quantity H, if you write it in terms of the px's instead of the x dots, then it's called the Hamiltonian. And that's what appears in quantum mechanics, and what we'll spend the rest of the course discussing at length. So on Thursday, I would like to finish the the chapter. There's only one more topic, and that topic will not be on the exam. Then you have the assignment due on Friday, and I have one example on the routine, but I don't have many examples to work through, so I'll just be available to answer questions related to the assignment or studying for the exam. But remember, the next Tuesday we'll have a special session dedicated to studying for the midterm. Any questions? Okay. If there's no questions, then we'll talk again on Thursday. Thanks, everyone. Bye.